Hello everyone, and welcome back to my BPHO video series. In this video, we are going to tackle question 1G from the 2018 British Physics Olympiad. Let's dive in. First, let's read the question. A thick-bottomed cylindrical glass beaker is placed on a bench. Water and oil are poured into the beaker and form distinct layers, as shown in the diagram. The bottom of the beaker is 1.8 cm thick. The water layer is 1.2 cm deep, and the oil layer is 0.8 cm deep. The question has two parts. Part 1. Draw a diagram showing the path of a ray at a small angle to the normal, traveling from the underside of the beaker and being refracted through the layers. Part 2. Assuming the angles of deviation are small, calculate the apparent vertical displacement of the lab bench when viewed from above. The refractive indices are 1.5, 1.3, and 1.1 for the glass, water, and oil, respectively. Let's begin by drawing a ray diagram to visualize what's happening. We consider two typical rays coming from a point O at the base of the beaker. The first ray travels vertically upwards to the observer's eye. It does not bend because it is normal to the boundaries between layers. It excites into air at point E. The second ray travels with a small angle to the normal from glass to water, to oil, to air. At each interface, the second ray bends away from the normal because it's going into a medium with lower refractive index. From glass to water, the second ray bends slightly away from normal. The angle to the normal changes from Z1 to Z2. From water to oil, the second ray bends further away. The angle to the normal changes from Z2 to Z3. From oil to air, the second ray bends even more. The angle to the normal changes from Z3 to Z4, and it emerges into air at point R. When the rays come into the observer's eye, the brain assumes they are traveling in straight lines and traces them back along the final directions. So it appears that the rays come from point A, above the actual base of the beaker, and point A is the apparent position of the base. As shown in figure, we call the distance from E to A the apparent depth of the base. Now let's use the angles and distances in the figure to calculate the apparent depth. From the triangle AER, we can say that the total horizontal shift of the second ray from normal, labeled as ER, is equal to the apparent depth EA times tangent Z4, and the horizontal shift ER is the sum of all the small sideways displacements it undergoes at each interface, as shown in the figure. So it equals 1.8 centimeters times tangent Z1 plus 1.2 centimeters times tangent Z2 plus 0.8 centimeters times tangent Z3. Since the question tells us the angles are small, we can use the small angle approximation. Sin theta is approximately equal to tangent theta, so we can rewrite the equation as EA times sin theta 4 equals 1.8 times sin theta 1 plus 1.2 times sin theta 2 plus 0.8 times sin theta 3. Let's call this equation 1. And from Snell's law, the refractive index times the sine of refractive angle is the same across boundaries. So we get 1.5 times sin theta 1 equals 1.3 times sin theta 2 equals 1.1 times sin theta 3 equals 1.0 times sin theta 4. And let's call this equation 2. Now, dividing equation 1 by equation 2 eliminates the angles and allows us to directly solve the apparent depth EA. So the apparent depth EA equals 1.8 divided by 1.5 plus 1.2 divided by 1.3 plus 0.8 divided by 1.1, which is 2.85 centimeters. And the real depth is the sum of all three actual layers, 1.8 plus 1.2 plus 0.8, which equals 3.8 centimeters. Hence, the apparent vertical displacement of the base is real depth minus apparent depth, 3.8 minus 2.85, which is 0.95 centimeters. And that's the answer for the question. Thanks for watching. I'm Felix Weichel, and I will see you in the next video.